Greetings. This is a CyberEye broadcast updating you on the latest and greatest developments in the world of science and technology. Silicon semiconductors have taken a dazzling distance along the computing road. But even if they continue to get faster and more powerful, there's a limit to what classical computing can do. The next level in computing is quantum, tapping the quantum mechanical properties of materials to process information in ways that will make today's fastest supercomputers seem like pocket calculators. And for the first time, scientists, at places like IBM, are moving beyond just theorizing about them to actually envisioning how a finished quantum computer would work. In labs across the globe, the first building blocks of the first quantum computers are slowly becoming real. The idea of quantum computing was introduced in the early 1980s by physicist Richard Feynman, and the field is still very much in its infancy. But as a discipline, it's turning a critical corner as the theoretical interconnects with the practical. There's more than one way to build a quantum computer, and it's still far too early to know which, if any, of these approaches will produce a working system. But between all of these varied approaches to tapping the quantum world, there's one common thread: it's all about the qubit. Unlike a bit, a qubit can exist as a 0, a 1, or in a state of superposition, which basically means it is both a 0 and a 1 at the same time. This is part of the quantum properties, where things are anything but intuitive. You start with a sea of all possible answers in your quantum states, and you design your algorithm to peel away the wrong answers so that the right answer emerges, says Matthias Stephan, manager of the experimental quantum computing research team at IBM Research. Rather than considering one solution to a problem at a time, you can consider multiple possible solutions simultaneously. Researchers at the Air Force Research Lab, AFRL, have described a novel way to build a simple quantum computer. The idea, rather than using a set of not always reliable interferometers to measure the inputs and outputs of data encoded in photons, they want to freeze their interferometers in glass using holograms, making their properties more stable. That way, researchers could stack the holograms to perform simple quantum functions without worrying about them losing their properties. Quantum computing requires encoding information into a quantum medium, and light is the most obvious choice. Photons don't have mass and therefore don't interact much with external forces. Things like electrical interference or magnetic fields do not interfere with a quantum state, and photons travel straight through transparent matter. But light is also a bit tricky, because photons don't interact with each other well either. Processing information in a photon at the receiving end can be particularly problematic. Another exciting step forward is the NIST simulator, which is simply a single layer of beryllium ions, hundreds of them stretching across a circular plane less than 1 mm in diameter, hovering inside a chamber known as a Penning trap. The quantum bit in this case is the outermost electron of each ion. By cooling the ions to near absolute zero with a laser, and then hammering them with carefully timed microwave and laser pulses, the NIST physicists are able to get the electrons to interact in controlled ways that mimic complex quantum systems that can't be studied practically in the laboratory. Thus, it's more a quantum system simulator than a true quantum computer. The NIST reports, though in order to benchmark their creation, experiments had to be carried out with relatively weak interactions between electrons, since the system had to be simple enough to be confirmed by a classical computer. To check the efficacy of the first quantum computers, or simulators, scientists will need a working quantum computer, a paradox that is going to lead to some fits and starts along the way to building a true quantum computing platform. Because of the many considerable challenges, most researchers are starting small, pouring their brainpower and research dollars into developing a single, stable qubit, and eventually strings of tens, then hundreds, and then thousands and tens of thousands of qubits. Update complete.